So tomorrow we are going to have a lecture from today's lecture. So please be attentive. Artificial neural network is the next topic, and as you will see, it is based on linear regression and logistic regression that we have studied, and we have also done the labs related to that, and also I have uploaded some sample questions. So hopefully those things are clear to all. So the outline of today's lecture would be as this. Okay, we're starting with the neuron or perceptron, which is the basic building block of the neural network. Uh, After that, we're going to look at neural network, and basically that will be stacking perceptron. So whatever we learn here in neural network, we are going to stack them together to build a network of neurons, and that will define the artificial neural network, or we can also call it deep learning. Loss minimization, and as in the case of linear regression and logistic regression, once we have the hypothesis, the next thing we do is to define a cost function and then minimize that cost function using gradient descent. The same approach will be followed here. The next is then we're going to look at the implementation of ANN and how to use PyTorch to do that. You have already done that in the labs, but I'm briefly going to go over it again to revise some of the things. And just to give you a bigger picture where we are, so as I have done this numerous times, we are in the supervised learning domain. And in supervised learning domain, this is the training data that you have. So you have n training examples, and in supervised you will have the target. For all cases, you will have the target y. There are two types of supervised learning. One is classification, the other one is regression. In classification, this y, the target label, that is discrete. For example, if you want to classify the x into 10 classes, like you did in the MNIST dataset, that is a classification problem. The other is regression, where y is continuous, and for example, you want to predict the price of the house given its features such as its area, its number of rooms, etc. That is the regression problem. And apart from many other algorithms, the ones that we looked that are relevant to today's topic, they are the linear regression and logistic regression. So linear regression is the regression algorithm, and logistic regression is the classification algorithm. So today we are going to, so basically artificial neural network is for both regression and logistic, for classification and regression both. But we are going to start or introduce this topic using the classification example. Okay. Okay, so after this background, let's start with the first part, the basic building block of the neuron, of neural network. The basic building block is called the perceptron. It is also called neuron, or to be more exact, it is also called artificial neuron. Okay? To distinguish it from the biological neuron. And as you will see, the perceptron, or the basic building block of the neural network, is what you have actually studied in the logistic regression. In logistic regression, my hypothesis function was this. Okay, this is my and in logistic regression we had sigmoid. So let me have sigmoid function here. So I applied sigmoid function to this W transpose X. And the second thing is this change of notation. We have been using theta to represent parameters, but we can also, in artificial neural network, mostly to use W to represent weights. So we use W to represent the parameters of the model. So, but you can use either of those, but I'm going to use in this lecture W. So and in the last lab also you studied, we discussed this. So if you want to draw this pictorially, what you're going to do is do something like that. So starting from the input, this is my input. So I'm going to first of all draw the input. ठीक है, and we are going to take the example कि आपकी input is two dimensional. So this is the first dimension, this is the second dimension, and this is your bias term, which is always 1. And then you have these parameters or the weights. The weights represents the value. I'm going to write it on the edges of this figure. So basically W0 will be multiplied by 1, W1 will be multiplied by x1, W2 will be multiplied by x2. And finally this part here, which I'm going to call the neuron or perceptron, is going to take the sum of these values. So basically what it is going to do is to compute multiply with x0 plus w1 x1 w2 x2. So it is going to take this sum. ठीक है, इंडिविजुअली यहाँ आपने मल्टीप्लाई कर दिया x1 1 को w0 से, w1 को wx1 से, w2 को x2 से, and finally over here you add them together. And once you add them, and that will be basically in vector form, you can represent it like this. Okay, so these w and x are vectors now. Okay, for example, w is a vector w0, w1, w2, and x is also a vector of input x0, which is always 1. Let me just write 1 instead, 1, x1 and x2. Okay. Now once you have done that, then you also need to apply some non-linearity, which in this case is sigma. So let me just denote it g, that you apply some function g on it, and this is your hypothesis. Okay. So all I have done is represent this hypothesis that was there in the case of logistic regression and drawn it using this figure. So whenever you see this figure, it should be immediately clear to you. This is the input layer, this is the neuron, and then you have the output layer. Okay. And for the artificial neural network, this is basically the building block. Okay, so this is basically your perceptron or a neuron, this part here, which is simply going to add the inputs after multiplying the weights with the input, and then apply some non-linearity, and that will define your output, or that we were also calling it the hypothesis. So we have discussed all these things, that x and y, they are vectors, and basically in the equation form this figure can be represented like this, and in the figure form this is equivalent. And this g is important. It's any nonlinear function. I mean, not any, but there are different types of these nonlinear functions that you can apply. They're also called activation functions. Why do we call them activation functions? Because they if remember in the sigmoid case also, on the x-axis, when you apply the sigmoid, if g is, instead of g you have this sigmoid, and on the x-axis if I draw wt transpose x, and now it will be something like that, right? That if w transpose x is less than -4, then almost or approximately you get 0 output. And similarly, if it is greater than 4, then you get approximately 1. And in between, you have this rising curve. Okay. And exactly when W transpose X is 0, you get the value of 0.5. So this output, or this G function, it is restricting the output within 0 and 1. If you get 0, you can say that your this neuron has not fired, or it is not active. If you get 1, you can say, okay, the neuron is active or it has fired. See, both these terminologies are used when you talk about artificial neural network. So that is why we are going to call this activation function. This non-linearity that we apply, this G, we are going to call it the activation function. And briefly, let's look at the comparison between, or the similarities between the biological neuron and the artificial neuron that we just discussed. So basically this artificial neuron is modeled after the biological neuron. The brain, the basic building block of the brain is also a neuron, which is shown here in a very simplistic way. This is your cell body, similar to our cell body, okay, our neuron. Then you have some many inputs coming to your neuron, and just like here we have inputs that are coming into the neuron. Then the neuron, the nucleus or the cell body does perform some function, whatever that is, and it outputs some value. Either it fires or it does not fire, and whatever it outputs, then it is connected to other neurons. The same is here. We perform some action. We take the what we do is take the sum and then apply the non-linearity or an activation function, and then we have the output, and then this output would be connected to different neurons. Later on we will discuss that. So this is the similarity between the biological neuron and artificial neuron. So basically, artificial neuron is modeled after a biological neuron in a simplistic way. I mean, the biological neuron is much more complex than what we have. Okay, so the activation function is important. The activation functions are mathematical equations that determine the output of the neural network. Activation functions allow to introduce non-linearity into the network. And what will this non-linearity help us in? It will help us in getting non-linear decision boundaries. For example, if you have a data set like this over here, then you can see there are two classes, green and red, and a linear line or a linear decision boundary will not be able to distinguish these two classes. For that, you need to have a non-linear boundary. So if you do not have these activation functions, these non-linearity applied to your neuron, you will never be able to get a non-linear decision boundary. And it's not just the activation function. You also need to add more layers and stack multiple neurons to get a nonlinear boundary. But this activation function is also important. And so there are multiple options that you have that you can use for the activation function. The sigmoid you have, so far we have been using sigmoid, or you can also call it logistic function, and the equation for that is 1 plus e minus z. So z is the input. In our case, the input, what is the input in our case? In all cases, the input would be w transpose x. Okay, that would be your input. This is the linear input that goes into the activation function. And this we have already studied in detail. It is going to restrict the values between 0 and 1. So if it is less than 0.4 or maybe -5, you get 0. If it is greater than 5, you get 1. And intermediate values is this curve like this. Tan h is another one. It is going to restrict values between 1 and -1. So different applications. Right now we were discussing logistic regression, where the output was we wanted the output to be a probability. So that is why we use sigmoid. But in other cases, getting a output which is zero, which has zero mean, like here the mean is 0, that is much more beneficial. So in depending upon the application, depending on what you're doing, classification, regression, so TANH can be used. So we are going to actually discuss that later on when we discuss some practical matters, that how do you decide what activation function to use. But right now, we can go with sigmoid or any of one of these. Then there is this one is also quite often used, rectified linear unit. What this is going to do is that when your input to the nonlinear function, input basically remember is w transpose x. If w transpose x is less than 0, the ReLU or rectified linear unit is going to output 0, which means that the neuron will not be active, it will not fire. If the value w transpose x is greater than 0, it is going to output the value, whatever that value is. So that is why this is the curve we get. Okay. So this is rectified linear unit. Softmax is very similar to rectified linear unit. The difference is that this sharp transition from 0 to 1, over here is more smooth, much more smoother. You can see this, it is much more smoother here. But other than that, it is similar to ReLU. Leaky ReLU is also similar to the ReLU in that it will not output only 0 when W transpose X is less than 0, but it is going to give you some negative number, small number, but it will not be 0. So all these are used in different situations. Right now we are not going to discuss that, but when the time comes we will discuss के कौन से situation में कौन सा बेहतर है. Okay, so then some equations. Sigmoid you have already looked at. Rectified linear unit is max x z0, which basically means max of z is always this thing. So whatever max of either you get 0 or you get W transpose z, depending on if W transpose z is greater than 0. Then you have the equation for soft plus also here. Okay, any question? Let's move forward. Let's look at some of the examples. Let's see कि जो अब न्यूरॉन है, जो परसेप्ट्रॉन जो हमने डिस्कस किया, बेसिक बिल्डिंग ब्लॉक. Let's look at some of the examples, functions that it can predict rightly. The first that we're going to look at is OR function. I mean, these are simple functions, so we are going to look at them. क्या ये with different weights, how will it represent these functions? ठीक है. So this is the basic neuron, and these are my inputs. One is bias term. Then since in OR function only takes two inputs, so x1 and x2, and then it's going to produce some output. And this is the ground truth, that if 0 0 is given, it should output 0, and in all other cases it should output 1. This is the definition of our OR function. Now these weights W0, W1, W2, which we have to learn using gradient descent. Let's say we are given this after learning through using the data set, we have come up with these weights: -10 for W0, 20, and 20. So if we have these weights, let's see whether we are able to predict. Let's see if we are able to predict the this function or function. Okay, so let's look at the first example. So one starting with W transpose X. What will W transpose X be for the first example? W transpose X. Hassan, Javed. Hamza, Amjad. Okay, please show some response so that I am also motivated to teach.
Sir, initially
And
तो 0 से start होगा.
तो -10 आंसर बनता है इस सिनेरियो में.
ठीक है -10. Why is that? क्योंकि आपका x1 x2 0 है. x1 x2 when multiplied by 20 20 will be 0. Only this is 1, so you're going to get -10. And once you apply the sigmoid, and we know that this is the definition, this is the or this is the equation for the curve for the sigmoid, and you can easily see that the sigmoid when the value is greater than 5 is 1. Sigmoid when the value is less than -5 is 0. So the value is now, since you get -10, this value, your model is, or your neuron is predicting 0, which is right. Similarly, if we look at next example 0 1, your W transpose X will be
10
10. ठीक है, क्योंकि आपका x2 20 है और ये तो आपका 0 हो जाएगा, and 20 minus 10 will be 10, and when you apply sigmoid it is going to give you 1. And similarly for the example, so with these weights we can rightly predict the OR function. So let's look at AND function. With AND function, we have a situation whenever there is 1 and 1 as input, you get 1, otherwise you get 0. So when we use these weights with the same neuron, minus 30, 20, and 20, then this neuron is predicting the AND function. For example, let's start with just look at this example. For this case, W transpose X will be 20 minus 30 minus 10, right? And therefore your prediction would be using applying sigmoid, it is going to get to 0, which is right. And so with these weights, you can check for other values as well that we are getting the right answer. Now let's move on to another case, which is the XOR or NOR X NOR function. And we can easily, or we can let's first draw these data points. This is x1, this is x2. This is 0 0, it lies somewhere over here. This is 0 0 1 lies somewhere over here, which is 1. Okay, this is data point which is 1. 1 0 lies here, which is also 1, and 0 1 1 lies here, which is 0. Now you can easily see that in order to classify these 4 points, we cannot classify them using a linear line. No matter what how you orient the line, we will not be able to separate the ones from the 0. So this function cannot be represented by the basic neuron, because the basic perceptron can only give you a linear decision boundary, right? So as we discussed before, what we are going to do is to stack the neurons together and build a network of neurons, which we are going to call the artificial neural network. Okay, so that is what we are going to do. To get non-linear boundary, we are going to stack different neurons together, and then we will see for this case also and for other cases also that we will be able to get a non-linear boundary. So this is what we are doing by stacking the different perceptrons. Okay, so this is one example of stacking different. This is one architecture of stacking different neurons. So, or maybe I should draw here before we move on to that, and draw step by step. This is, and by the way, these are very important topics. If you are, if you have a little bit of interest in machine learning, I mean, not as a course, but later on for your as a your interest, then these are the important topics. Every machine learning, deep learning is built on these things. Okay, so this is my input, and this is one neuron that I have here. So this is neuron taking the sum, applying some activation function, and this is the output, and let me call it, let's say, x1. Now I can have another neuron with a different color, let's say with color blue, another neuron, and it is also getting the input from these from the input, and it is also producing an output which is h2. Okay, now of course both of these neurons have the input is same, but the weights will be different. So for example, I can write here, maybe I can write with yeah, with v, let's say this is weight 0, weight 1, weight 2. Similarly, for the first neuron, I have u0, u1, and u2. Okay, so this will give me two outputs. Now what I'm going to do is to create another neuron with green color, for example. This is another neuron here, and it is also doing summation, and this is G. And the inputs will not be, the input that are here, but the output of the neuron in the previous layer, that will be the input to this neuron. Okay, so this is the input here coming here, and similarly I will have then weights W1 and W2, and I can also have a bias term here also, just like I had there. So that would maybe W0. Okay, and now this output would be my hypothesis. Instead of the output in the previous layer, this will be my final hypothesis. So this is a neural network which consists of three neurons. This is the input layer, which is simply the input. It depends कि आपका input कितनी dimension है. It will be of that size, input layer. This is the hidden layer. Why hidden? Because you can see the input, you provide that, you see the output, but the intermediate layers you do not see. So we are going to call them the hidden layers. So this is hidden layer, and this is the input layer, and finally you have the output layer here. Okay, so this is output layer, this is hidden layer, and this is input layer. I have two neurons in the hidden layer, and I have one neuron in the output layer. This is example of single layer artificial neural network, and the output is also has only one neuron. Now, if I want to write it using the equation, the hypothesis, so I'm going to start with H1. H1 is the input vector X, or so now the parameter for this first neuron is U. So U transpose X, right? And U is a vector, remember, it is this vector U0, U1, U2. And X is also a vector, so I can maybe write it bold. X is also a vector with components 1, x0, and x1. Similarly, the second neuron, this is the V. Second neuron, the weight vector is a V, so W transpose X. And my final hypothesis, which maybe I can call H simply without any subscript, or maybe I can call it H3 also. Or to distinguish it from, maybe probably what I should do is to call them F1 and F2. F1 and F2, and this is then the final output. So this is F1 and F2. So final H would be my weight vector W, and times it. Now in this layer, since the input is not the input layer, but it is the output of the second of the hidden layer, so the input is basically 1, which is bias term, and F1 and F2. Okay, and F1, F2, as you can see, are these functions. Actually, I have not applied the sigmoid here, so these are contain G as well. Over here also you have the G activation function. So this is the output or my hypothesis now. So everyone is clear about the very simple example of a neural network. What we have done is added a hidden layer with two neurons, connected them to the input. So each edge or each connection, each one of these connection will have a corresponding weight. And similarly, we have an output layer which is connected to the hidden layer, and for that we also have the weight. So now when we try to learn the weights, we have to learn all these 9 weights. Okay? U0, U1, U2, V0, V1, V2, and this one here, and W0, W1, and W2. So we have to learn these 9 weights. Once we know these 9 weights, then we can easily make the prediction using these 9 weights. Okay? This is all we need to make the prediction. And as we did in logistic regression, that if you have instead of a binary classification problem, you have a multi-class classification problem, then you will have then you require that many output. Remember, when we looked at multi-class classification, Then we said if you have 10 labels, then the output must also have 10 labels, or it should your hypothesis must also output 10 values. So how we will represent that? I mean, it's easy. We will add that many neurons in the output layer. For example, here it was for binary classification. For binary classification, you just need one output because the probability for the for not for the zero class will simply be 1 minus the probability for the one class. But if you have, let's say, three classes, then you need to add three output neurons here. So maybe black color. This is another class, and these are its weights. Similarly, we need to add another one, or maybe with a different color. Yellow, and so now we're getting three classes as output. Okay, and of course then you will have h1, h2, and h3, and each one will have different weights. So by adding different classes, you have added more weights as well. So this is an example of a single layer multi-output neural network. In this case, we have, let's say, I have only drawn true, but you can have as many classes depending on the data set you have. If you have 10 labels, you will need 10 neurons in the output layer, and so on. And that is not all. What you can do is to add hidden layers, more hidden layers as well. Okay, for example, let me give you an example here. This is your input layer, for example. Then you add two hidden layers. So this is first hidden layer, this is second hidden layer, and this is the output layer. Okay, this is input layer, this is hidden layer, these two, and this is the output layer. So this is connected here. So one of them is connected. थोड़ा सा ये figure खराब हो गया, लेकिन you get the idea. So investing stops us from adding more hidden layers. You can have add two hidden layers, three hidden layers, four hidden layers, five hidden layers, and similarly, nothing stops you from adding more neurons in a hidden layer. You can have three neurons in one hidden layer, four neurons, 10 neurons, 100 neurons, and similarly in the next layer you can have 10, 25 hidden neurons. So all these different combinations you can have. So these will define your architecture, and there is no hard and fast rule that how many layers you should have, how many neurons in each layer you should have, and so all these are up to the problem that you have and up to the it's basically by hit and trial. There are certain guidelines, but apart from that, there is no hard and fast rule in choosing these values. And when we talk about the deep learning, so what we are basically referring is the number of hidden layers that you have. The more hidden layers you have, the more deep your network is, and basically, the depth of the deep learning algorithm is dependent on the number of hidden layers that you have. And of course, when you add more hidden layers or you add more neuron in a layer, what you are doing is you are adding more weights. So in return, you have to learn more weights also. So only if you have a huge data set, you are going to get reasonable values for the weight vectors, for the W's. Otherwise, your model may not be able to learn, or it may overfit. So we will discuss these guidelines later on. Okay, how many neurons layers you should have and stuff like that. And they will be based on things like how, depending on your data set and other things. But in the end, it will be in the end it will you can restrict certain number of options, but from those options, selecting the optimal one will be based on hit and trial. Okay, so this is the general case. The input layer, many hidden layers, and the number of neuron hidden layers, that is also variable. Maybe you have 10, here you may have 20, and so on. And then this is the final output layer. And yeah, so this is how you build a artificial neural network. Okay, let's look at this example that we studied before, and then we will take a break and then come back again. This is the same example, x nor. This is non-linear function, and of course we saw that the single neuron is not able to predict the right values. Now we are going to stack different neurons. In the hidden layer, we have two neurons. One is this neuron, this is the other neuron, and we have also specified the weights. So for the blue one, we have the blue weights. For the red one, we have the red weights. And these two neurons, these are the same numbers for the and nor function. So these two neurons, they are predicting the and nor function. So this is my input now. Okay, and the first neuron, this blue one here, this is and function, so I'm getting 0 0 0 1. The red one is nor function, I'm getting 1 0 0 1. And using these values you can double check also that whether you are getting these values or not, but for now you can go with my word. And finally, I have another neuron in the output layer which takes input from the hidden layer. So with these values, with these as input now, when you compute the, where is it? Okay. With these as input now, these two columns now, and you take the OR of these two columns, so this is what you get. 1 0 0 1, which is the X OR function that you want to predict. So by stacking these neurons, we have been able to get a non-linear boundary. Okay. So right here, in this example, I have supplied you with these weights, with these 9 weights. But in the actual problem, you will be given a data set, this x and this final y. So this is x, this is y. And using your data set, you have to find these weight vectors, these w's, these weights of the edges. And we are going to use the same approach, define a loss function, compute gradient, and then use gradient descent to update the parameters. Okay, the remaining structure of the program will remain as you have done in linear regression and logistic regression. Any question? Okay, so we take a break and we meet at 3:10 or 3 maybe 3:15. Okay, we meet at 3:15. Okay, Bismillah Rahman Rahim. Let's continue with the lecture. Okay, so as we discussed that, am I audible and screen visible? Just to confirm.
Yes, sir.
Okay, thank you. So as we discussed, this is a linear, one example of a artificial neural network. And now the objective is to find these weights. And the way we are going to do that is to define a cost function, which we can use the same that we had for logistic regression or linear regression. And then we are going to compute the gradient descent, the follow the gradient descent algorithm. And the main thing is, remember, in gradient descent we repeat this part or update the parameters, these weights, using this equation. That wj, the old value wj minus the learning rate and the partial derivative of the cost function with respect to the weight. So now we are going to actually focus on this one here. How do you compute these derivatives? Because before we had just one neuron, it was easy to do that. But now let's say if we want to update this weight, then this weight will depend on this weight as well. And similarly, if you want to update this one, it will depend on this one. And in more complex architecture where you have multiple hidden layers, so they will have this, this dependence will be on a multiple layers. So to compute, how do you compute gradient descent, or how do you compute these partial derivatives? That is what we're going to discuss next. So starting from loss minimization, the objective is to minimize loss subject to or based on choosing the right value of the weights which minimize our loss function. This is my training set, and this is the objective, and this is my cost function. So I sum over all values of my training set, and this is the loss on one particular example of my training set. And so once I have the once I have this, so this right in this slide I'm just setting up the optimization problem. Then this is my training set, this is the cost function. The goal is to compute the gradient of my cost function with respect to my weights. And once I have that, I update the using gradient descent, update the weights. So what kind of loss functions I can use? We have been using two loss functions. This one was for regression, the mean square error loss, loss error, simply the prediction of my network minus the ground truth and taking the square. Then the other one was for binary cross entropy loss. For binary classification problem, this was the loss that we considered. Okay, this is for classification. So we discussed both of these loss functions in detail. Specifically, we looked at each part of this loss function when we talked about logistic regression. So once we define the loss function, then the objective is to actually compute this gradient. Okay? And as I discussed before, when you have a deep neural network where there are multiple hidden layers, then we have to use chain rule to compute the gradient descent or to compute the derivative. And And in order to understand this chain rule, we're going to start from the basics. We're going to look at how do you compute derivative of a single function, how do you compute derivative of a composite function, and so on. And then we will see that how to compute the derivative of a neural network which has multiple layers. But as you will see, it's not difficult. You just have to follow me. Okay, we are going to start from the basics, and the basics, once we understand them, then computing the derivative using chain rule would be simply a matter of multiplying different derivatives at each layer. Okay, in order to do that, let's start by looking at a box diagram, or this diagram here of a function. So what is a function? You have a function, there are certain input to the function, and for example in this case you have in one in 2, and in 3. And then this function produces some output which is called out. So in a figure form, we can represent it like this, that this is my function. These are my inputs in 1, in 2, in 3, and this is my output. Okay, the output. So what I'm going to do is to write the derivative of a simple function on the edges of this diagram. For example, let's consider a example that I have a function 2x. This is a function. If I want to draw it in a figure form, then this is my function f. There is only one input in this case, which is x, and this is the output, right? And on the edges, I am going to write the derivatives. What is the derivative in this case of the simple example? It is 2, right? Because if you take the derivative of f with respect to x with respect to the input, derivative is 2. So on the edges, I'm going to write the derivatives. So what this 2 is telling me, that if I change x by 1 unit, my output is going to change by 2 units. For example, if x is 1, my output is 2. If this is 2, it is 4. If this is 3, this is 6. So this is how my output is going to change. So this 2 is telling me that. If I have a function which is x square, in that case, for this one, my derivative would be 2x. So that is how my output is changing with respect to the input. Okay, so let's look at some other simple examples of a function. So this is one example, the first figure, where the function is simply adding two inputs. So I have two inputs, a and b, and the function is a plus function. It is simply adding two values, right? So what is the rate of change of f with respect to the first input? It is equal to, this is the first input, a. The rate of change of f with respect to a is,
1.
okay, 1. So I write 1 on the edge here. Similarly, the rate of change of f, or the derivative of f with respect to b, is also 1. Okay, so I have written that on the edge. For a function which is subtracting the values, the derivative with respect to b is -1. With a it is 1, so I have written 1. With b it is -1. Okay, very easy. Okay, so yeah. The third function that we are considering is the multiplication. This function is going to simply multiply two values, a to b. Now here, if I compute the derivative with respect to a, it will be equal to, what will this derivative equal to?
E.
Okay, b.
7 sigma.
That is why I have written on the edges b. Similarly, with respect to b is a. Okay.
Yes, sir.
Okay, so let's move forward. So what we are doing essentially is looking at simple functions, because in the end the neural network is also uh, a network of these simple functions. So once we know derivative at each of those steps, we can then simply compute the overall derivative, as we will see in the next slide. So we will also encounter a max function. What max function is doing, it is simply computing the max of two values. If a is greater than b, the max function is going to output a. If b is greater than a, then it is going to output b. So if I want to compute the derivative of f with respect to a, of course it will be 1 only if a is greater than b. Because if a is greater than b, then the output of this max will be a. And if I compute the derivative of f with respect to a, it is 1. But if b is greater than a, then this function will output b, and the derivative of f with respect to a will be 0, because that is not in this equation. So in order to represent this ones and 0, I'm going to use this indicator function 1. 1 is indicator function. An indicator function is such function that the argument, if the argument is true, it is going to output 1, otherwise it is going to output 0. So if I write a greater than b, so this function, this indicator function is going to output 1 only if a is greater than b, otherwise it is going to output 0. Similarly, this indicator function is going to output 1 if a is less than b, otherwise it is going to output 0. So that is what I want actually also. If a is greater than b, then I want to have then the derivative of f with respect to a is 1. And if a is less than b, then the output is 0. So that is why this is the derivative of f of this function with respect to a. It will be only 1 if a is greater than b, otherwise it will be 0. Over here, if this is the derivative. Any question up till now? Okay. Let's also consider the sigmoid function, because in your network, this sigmoid function is also available. There is the input to sigmoid function is just one input. And so remember, this is the sigmoid function. A is the input, and the sigmoid function is computing this value. And rate of change of this sigmoid function with respect to a is equal to, so I'm not going to derive the derivative, the gradient of this. I'm simply going to write the value, the derivative. You can search online to look at the derivation. For this, I mean, for the course, we just need to know, okay, what is the derivative, and this is basically sigmoid of the input 1 minus sigmoid of the input. So this is the derivative, and that is what I have written over here. Okay. So so we know now that the derivatives of these simple function are like this. So let's also discuss one more function, log, because remember the logistic regression loss function also contains this function log. So we need to know the derivative of this function as well. So log, the input to that is just one. There is just one input to this function, and the derivative is simply 1 divided by the input. Okay. Okay, so far so good. So far we have only looked at simple examples, which we have only looked at functions and not the composite functions. What happens if we have a situation like this, that we have a function 1 which takes some input, it produces the output which we are calling it mid, and this mid is then is used as input to a second function over here, and then the second function produces the output, and the objective is to find the overall derivative, which means that the rate of change of the output with respect to this input. So that we can compute by only looking at this function and compute and writing the derivative, then only considering this function and computing what is the derivative over here, and finally the overall derivative would be to multiply these two derivatives together. Okay, as we have done it over here. But this is simply the chain rule that we have been using, or you must have used in your first semester calculus or in the second semester. So the idea is that if to you know to know these simple derivatives, and then you can use these to build the overall derivative of the output with respect to the input. For example, let's have an example over here. Okay, let's do that for the case when you have h of x minus y square. This is for linear regression, right? And let's compute the derivative of that, which we already know. I mean, this is a very simple case, but let's do it in a way using these block diagrams. So let's start by actually representing h of x. You know h of x is equal to the weight w. There are two inputs and x. You multiply them together, right? And then you apply the sigmoid. That is going to give you h of x, right? Okay, this is basically the sigmoid applied to W transpose X. Actually, sorry, this is linear regression, so we do not apply the sigmoid. We just have W transpose X, so no sigmoid here. Or maybe I think we let's look at a little bit difficult case than the simple, because this we can easily compute without actually looking at these block diagrams. Let's look at this example over here. So this is the example. This is the case. This is also very simple in the sense that it also consists of only one neuron. But the loss function is a little bit more complex than the loss function for linear regression. So this is my loss function for logistic regression, right? And let's break it into two parts. This is L1, this is L2. If I want to compute the derivative of for this part, that is what I'm going to do. This h of x is W transpose x. W, you can write W or you can write theta. So in order to represent that, I have done it over here, this portion. You have the input, first input, second input, you multiply them together over here, and then you apply the uh, the sigmoid to it. Okay. Let me actually do that here again, just to make things easier. So this is W, this is X, you multiply them together and then apply the sigmoid. This defines your H, your output. Then you apply, in order to compute the, because we have to compute the derivative of the loss with respect to W. So then you apply the log of h of x. So this you have log here. And finally you multiply by minus y. This is your overall loss for this L1. Now we have to compute the derivatives on the edges. Okay, which means that once I am computing the derivative of this portion, I just focus on this portion only. I know this is the multiplication, so for multiplication I know the derivative of L1 with respect to this input is equal to minus y, right? Back, we can easily see that if there are two inputs, the derivative of the output with respect to this input is b, which is the second input. Okay, so that is what I have done. On that case, minus y is the input, so I have written minus y over here. And similarly, I don't need to write anything over here because I don't need to compute the derivative on this side of the graph. This is the log function, and the log function is 1. The derivative is 1 by h. Here now I'm focusing only on this function here. Now let's focus on the function which is the sigmoid, and as we discussed, the sigmoid, is the derivative is this part here. So uh, the output 1 minus the output. Yeah, that is what I have done over here. This is the output, 1 minus the output. The output here is h, so h 1 minus h. And over here again I have a function which is multiplying two values. The derivative of the output with respect to w is x. Okay. So abhi one so I know I have written the derivatives on all the edges. Now to compute the derivative of L1 with respect to W, so this is L1, this is W, I simply have to multiply all the derivatives along this path which connects L1 to W. Okay. And so starting from the top, minus y times 1 over h times h 1 minus h times x. Okay. Or once you simplify this, so you are left with minus y 1 minus h x. And similarly, you're going to do the same for the second part of the loss function. You're going to get a different value. You're going to add these two values, and this is the overall the derivative of L with respect to the weight parameters. Okay. So as you can see, by using these block diagrams, things have become easier. You just have to compute the derivative on that portion, and then finally using chain rule you multiply all the derivatives to get the overall derivative. And remember, we are going to have a quiz next class from this topic, so you must practice this at home. Any question from this example before we move forward?
सर आज के लिए सर बहुत नहीं हो गया, अभी फॉरवर्ड मूव ना करें
जी
सर। आज के लिए बस कर दें कि कल क्विज लेना है?
ठीक है, आज के लिए बस कर दिए, बस ये तो आगे चीज़ हमने पढ़ी हुई है. So once you know the derivative, then you follow the approach जो आपने gradient descent में की थी. That algorithm is basically called generalized back propagation algorithm. ठीक है, इसमें वही forward pass है, वही backward pass है. Forward pass computes the output of the network. Basically you feed the input जो भी आपने example pick की, you put it into the network. You have the weights from the previous iteration. You use those weights to compute the output. And then you do the backward pass, which is going to compute the gradients. Because backward pass simply means that you multiply all these derivatives to get the gradient. Once you do that, then you perform the step, which is simply update your parameters using the derivatives wj. ठीक है, this is generalized back propagation algorithm जो अपने lab 3, 4, 5, 6 सब में आप करते आ रहे हैं और 4 से आगे. And this is also from previous lectures, batch gradient descent, stochastic gradient descent, everything remains same. The whole structure of your algorithm remains same. You have defined the hypothesis. Abhi aapka hypothesis, instead of a single neuron, it is a network of neurons. So baki algorithm remains same. You define loss function and then minimize using gradient descent. Then there are two options. You can either choose batch gradient descent or stochastic gradient descent. And we know कि batch gradient descent और stochastic gradient descent में क्या फ़र्क है. ठीक है, तो this slide is just simply a revision of that. Okay, so this we will cover tomorrow. And any question?